Okay, so welcome back to part 2 of lecture 13. Um, I was discussing with you the postulates about the observables. So we have seen that an observable must be represented by a Hermitian operator. And once you have uh, the operator itself, you can compute the eigenvalues and the eigenstates associated with this operator. And the eigenvalues are the possible values of the physical quantity we're looking at to be measured. And the eigenstates are the states at which, if you measure the outcome in this state, you always get the corresponding eigenvalue. So these are states with well-defined outcomes in the measurement. So you get always the same value if your system is in the eigenstate of an operator, and if you measure this operator, of course. Okay. So what I want to do next is to, well, it's loading. Okay, it's working now. I want to construct explicitly an example of an observable. So we have discussed a lot in this course the linear polarization of a photon. So we have seen that we can observe the polarization of a photon in a direction theta if we pass it through a polarizer in the direction theta. So how this helps us? Well, if you have a photon that is prepared in a state of polarization theta, and you have a polarizer in the direction of theta, you know that if you send photons against this polarizer, all photons will cross it. Okay? So you're going to detect photons on the other side of the polarizer with 100% of confidence. Okay? So we say that the probability of seeing a photon on the other side of the polarizer is 1. However, if the state is theta plus pi over 2, namely, if the photon now is prepared in a state that is orthogonal to the direction of the polarizer, you know that no photon will cross the polarizer. In other words, the probability of seeing a photon on the other side of the polarizer is 0. Or you can phrase it differently. The probability of not seeing a photon on the other side is 1. Okay? So you can make these statements mathematically by defining an observable that is what we call the observable that measures the polarization of the photon. Okay? So P hat with the subscript theta is the observable that tells you if a photon has polarization theta. Okay? So, well, you know that I have two states which are orthogonal that essentially can be used as a basis for this operator. Okay? So what I'm doing here, I'm just writing P hat theta as the sum of the outer product of these vectors that form a basis. So the first vector is the vector theta. Okay? So if my state is prepared in the state theta, then the polarization will be theta with 100% of chances. And the state theta plus pi over 2 is a state which the polarization of seeing the photon with polarization, the probability of seeing the photon with polarization theta is 0. So I have two eigenvalues. I have 1 or 0. This is exactly what we use to say if the photon is polarized in the theta direction or not. 1 or 0. Okay? So I write this as 1 times the outer product of the eigenvectors that corresponds to this number, namely theta, plus 0, which is the eigenvalue corresponding to the state that gives me 0 chances of seeing the photon with polarization theta. So I'm just expanding my operator, my observable, in a spectral decomposition of it, where I have 1 times the first outer product of the vector basis plus 0 times the outer product of the second eigenvector. Okay, so this is very important now because you see that this operator will have either eigenvalue 1 or eigenvalue 0. But you see that I'm multiplying 0 by this thing. So 0 times this operator will give me just the operator 0. Okay? So p hat theta reduces to the outer product of theta. So p theta is just this. But we know how to write the cats associated with the state theta. This is cosine sine, and the bra is cosine sine. So I can multiply these, and if I multiply these guys, I will get this 2 by 2 matrix. You see that this is obviously Hermitian because all entries are real, and the off-diagonal terms, they are the same. So this is a symmetric matrix. And you see that the diagonal entries are real as well. And then I give you this exercise. You can compute the eigenvalues and the eigenvectors of p theta. So this is an exercise that you can do. And you see that the eigenvalues that you're going to get are 0 and 1. Okay? This means that the measurement of your the outcome of your measurement is either 1 or 0. So I see photon or I don't see photon. So this is represented by 1 and 0. This is exactly the same language that is used in quantum computing. So in quantum computing, you have a state that is either, so you have these bits, which are qubits because they're quantum bits, that when are scalars, sorry, let me read the question because it disappeared. Are scalars, so here I have a coefficient 1 and here I have a coefficient 0. 0 times an operator will be just 0, so I can neglect that. And 1, well, I just disappeared with 1 because 1 times n operator is just the operator itself. So the scalars are inside the discussion as well. Okay?
Yeah, hello.
Hi.
Yeah, please, I'm saying after multiplying by 1 and 0, and you do your simplification and you get let's say half outside the cos squared theta, cos theta, sin theta, everything in the 2 by 2, and you have half outside. Do I consider the half?
Which half?
I mean, after computing cos theta and I get half outside, do I consider it? I mean, not every question will be.
How do you get half from this multiplication? I don't understand that.
Okay, when the question is half cos theta sin theta, then if you take the conjugate, you get half cos theta and you multiply.
Okay, so you were asking if hypothetically you had a scalar. Here?
Yes, please.
Yeah, okay. No, the scalar should be here. Should be part of the operator. Of course, if it is just a global scalar, you can pull this out, but it should be here. Okay, so you don't neglect these scalars. Okay,
I see.
but look, a scalar is a more general thing than a phase. If you have a phase, a global phase, then these will automatically cancel out in this multiplication. Okay. Okay. So I was saying that, okay, there is something.
Hello.
Hi.
Please, can you repeat the explanation on the linear polarization, where especially the probability 1 and the probability 2?
Yes. So I'm saying that I want to write an operator, which is a 2 by 2 matrix. And this matrix will be an observable that tells me the following. Is the photon polarized with polarization, with linear polarization theta? Yes or no? Okay. So I have two vectors, namely theta and theta plus pi over 2, that I know the answer of the outcome of my experiment. If the system is prepared in the state theta, then the probability is 1. So the value associated with the measure is 1, and then the answer is yes. And I know another state, which is theta plus pi over 2, which the chances of being detected in the polarization theta is, the chances are 0. And therefore, you don't see any photons on the other side, and then you say that the answer is no. So
Okay.
this matrix or this operator will tell you if a photon crossed, then it will give 1, or if did not cross, and then it will give 0.
Okay.
These are
Yes.
the outcomes. And this is what I was saying about bits, because in computers, I mean, you use these bits, these pieces of information. That's, I mean, you can either flip it to 1 or to 0 in order to have an information. So you have a chain of bits that are either 1 or 0, and you encode information out of that. But now I can encode information using quantum bits. Namely, you have now a state which is not 1 or 0, but you have a state that is a linear combination of 1 and 0. Okay?
Wow. Okay. Thank you.
Yeah, you're welcome. Okay. Okay, good. Now I want to move to the uncertainty relations. This is a very important result in quantum mechanics. And today I will probably talk more about algebraic manipulations, and hopefully tomorrow I can give you more information about that. Okay, so I'll start with a basic statement, which is the following. The only situation in which the measurement of a quantity A has a result with complete confidence is when the system is in an eigenstate of the associated operator A hat. So if you have a state, and this state is the eigenstate of an observable, and you want to measure this observable, this is the only situation where you're going to get always the same outcome, which will be the eigenvalue associated to this eigenstate. Okay? So in this case, I can ask you, what is the expectation value of the operator A in the eigenstate little a, which is, you know, an eigenstate of the operator A with eigenvalue little a. So I write the expectation value in this eigenstate is represented by this. We already saw that. And since cat A is an eigenstate of big A, when I act with a hat on this cat, I will get the eigenvalue times the cat, right? By definition. So by definition, A acting on cat A is just the eigenvalue times the cat A. So when I act with a hat on cat A, I will get the number A times the cat A. But the number I can just pull out of my scalar product. Okay. So now I have a number times the scalar product AA. But since this is a state, by postulate 1 of quantum mechanics, this must be normalized. So this is 1. So the expectation value is just A. So this is just an obvious thing that says the following. If you are in an eigenstate, okay, then if you want to if you are in an eigenstate of an operator A and you want to compute the expectation value of this operator A in this state, then this will be equal to the eigenvalue associated with this eigenstate, which is just A. Okay? Good. But you see, I'm just saying that the expectation value in the state A is simply the eigenvalue. So I can rewrite the eigenvalue equation, which is this one. A hat acting on A is little a times the eigenstate A. I can just rewrite it as the expectation value of A hat in the state A times A, right? This is equivalent because this guy, the value of this guy in the state A is just little a. Okay? Given that equality, I can just bring this guy to the left-hand side and write A hat minus expectation value of A hat in the state A, this acting on the eigenstate A, and this must be 0. Okay? So this is what I'm writing here. If you have a state which is the eigenstate with eigenvalue A of the operator A hat, then this relation holds. Okay? Good. Now, if I prepare my system in a state which is not the eigenstate A, so now I have a system, and this is not in the eigenstate A. It's in a state which I call U. And if U is not an eigenstate of A, then every time that I measure A hat, I will get a different number, a different possible outcome of my measurement. And as you just learned, these numbers that you're going to get will be the eigenvalues of the operator A. Okay? So, in this particular situation, you have that the outcome of your measurement, which is little a, coincides with the expectation value of the operator. Okay? So you just see that the outcome is little a, the expectation value of your operator is a. And this happens just because the state is an eigenstate. Okay? But if your state now is not an eigenstate, then when you compute the expectation value of A in this state, you are not going to get that the expectation value of this operator in this state U will coincide with the values that you measured. Remember, the expectation value of an operator is the sum of the probabilities of getting an outcome times the corresponding outcomes. So you are weighting the sum by probabilities, and therefore you're not going to get the same result as just one outcome. Okay? So the result of the measurement that you obtain differs from the result of the expectation value. The expectation value is a fixed number. If I give you a state and I give you an observable, you can compute the expectation value of this observable in this state. And this is just a fixed number. But the result of the measurement, it can change because every time you perform the experiment, you get a different outcome. It turns out that this difference between the real value that you get from a measurement and the value, the expectation value of an operator, this difference is what we call a fluctuation. Okay? So, for instance, if well, we say that this must be taken with a grain of salt. Okay, we say that a good measurement of such fluctuations, namely a way of seeing if the outcomes differ too much from the expectation value, is using the so-called mean square deviation. So I define a quantity which is delta A U. So this you should read as the mean square deviation of A in the state U. And this is defined by the following. So the square of the mean square deviation is defined, look, by the expectation value of A hat minus the expectation value of A in the state U is squared. And this expectation value is taking the state U. Okay? It's not difficult to understand. Look, this represents just this operation here. I'm taking this operator, which is A hat minus expectation value of A hat in the state U. So this is just a number. And I'm taking the square of this. And I'm computing the expectation value of this new operator. This is what we call the square of the mean square deviation. Okay? Good. What is the nice part about that? Well, you see that when I compute, well, now I can expand. Okay, let me explain again as requested. So I'm just saying that typically in a measurement, you are not going to get outcomes. So the values of the outcomes will not be equivalent to the values, to the value of the expectation value. But you can compute the difference between these two things. And the difference is what we call is a fluctuation of of these values. So a hat acting on the state u gives you will give you information about the chances of getting some value aj, and the expectation value is when you average over all possible values. So I'm defining a quantity which takes this difference, so the difference of the measurement result with the expectation value, and I'm taking the square of that. I'm taking the square because I can have, for instance, I can have a hat minus expectation value of a hat as a negative number, so I square it to get just a positive number. But also, you see that if I expand this a hat minus a hat expectation value of a hat, well, a hat squared will be a hat squared minus, and then I have to take the product of these two guys. And you see that since this is a number and this is an operator, so this must be understood as a number times the identity operator. So this guy commutes with this guy. So I can simply write that the product of this guy by this guy and the product of this guy by this guy is the same thing. So I have twice, minus twice, because of this minus sign, expectation value of a times a. And finally, I have the square of the second term, which is plus expectation value of a squared. Okay? So I have this quantity here, which you see it's not trivial, right? So the value that you measure is not the same as the expectation value. So you should not expect this to be zero. Okay, I think there was a question about that in the chat. Yeah, so Mahmoud, this is not zero, okay? That's a very important observation. So this thing is not zero in general. It will be zero just in the situation that I described here. It will be zero when you are in an eigenstate of the operator. But in general, it's not. Now we can look at this expression here. So I have all these operators being sandwiched by the state u. So I have cat u here and bra u here. And I can just, this is a linear operation. I can just enter with the cat and distribute it to all different a's, and also with the bra. So the first term will be bra u, a hat squared u. So this gives this term. The second term will be minus 2, which I can pull out of my scalar product. Expectation value of a hat, which is also a number, so I can pull out. And then I'll have expectation value of u, a hat u. And then I get the second number. And finally, I have this expectation value squared, which is a number. So I can pull out as well. So this will be a hat squared times u bra u acting on cat u. So you see here that by definition, this expectation value of, so this is the expectation value of a in the state u, and this multiplies the expectation value of a in the state u. So this will be expectation value of a squared. But be careful, you take the expectation value and then you square. This is typically different from squaring the operator and then taking the expectation value, which is what we see in the first term. So the first term will be the expectation value of a squared in the state u, and I write it here. This second term will be minus 2 expectation value of a squared plus expectation value of a in the state u squared. So I can simplify one term here with one term here. Then I get this result. Okay? So the mean squared deviation of an operator A in the state U, the square of this quantity, is given by this difference here. All right? So now I can define what is the mean square deviation. The mean square deviation is just the square root of these two guys. So the mean square deviation of A in the state U will be the square root of this difference. Okay? There is a question in the chat. Can you explain again? Yes, sure. But you see that from this line to those lines here, I'm just working out an algebraic manipulation, right? I'm taking an operator and squaring it. So if I have an operator and I am taking the square of it, well, this is just, this guy times itself. So I'll have the first term squared. So you just think about a plus b squared. This will be a squared plus 2ab plus b squared. But here you have to be a bit careful because these are operators. Okay? So the first term will be a squared. And you just write a hat squared. The second term, well, here you have 2ab because you have numbers and they commute, and that's fine. You can combine the two contributions coming from a times b and b times a. But here they also commute because this is an operator and this is just a number times the identity operator. So you can write minus 2 expectation value of a in the state u, a hat. Okay? And finally, I have the last term, which is the b squared, which will be plus a. Okay? So just squaring this term will give me this contribution here. And now what I'm doing is that these operators, they are sandwiched by this state u. So I'm just applying the bra u and the cat u for each of these elements of my sum. So I will have a term that is bra u, a hat squared, cat u. And it is this term which, by definition of expectation value, this is nothing but the expectation value of the operator a hat squared in the state u. Okay? So this is just the definition of this thing. Okay? And I proceed in analogy to that. So the second term will be bra u, and then you enter with bra u here. There is a minus 2, it's a number you can pull out. There is an expectation value, it is a number you can pull out. And then you hit the operator a hat. So bra u acting on a hat. And this will be acting on the cat u. So you get this contribution here. And finally, you have this term, which is just a number. So when you take the bra and multiply by this guy, since this is just a number, you can pull out of the scalar product. And you're going to have the bra u acting on the cat u. And since you have bra u acting on the cat u, you have this thing here. But by postulate 1, this is a state, a quantum state, and therefore it must be normalized. So by the postulate 1, this is just 1. Okay? Good. Then you can just see that this guy will be the expectation value of a in the state u, and this will be a hat in the state u. All of it is squared. So you have this this guy here, where here I have a factor of -2, and here I have a factor of +1, so I have this minus, and then you get this result. Okay. Yeah, I mean, this is something that you have to reproduce by yourselves and be careful about all the comments. But I'm sure that this is not something complicated, and it's just about repeating it carefully. Okay. So then we end up with this definition of the mean square deviation of an operator in a state U. Okay. So this will measure how much how strong is the fluctuation around the expectation value of an operator. Okay. I think I'll stop here because we are already over time. So tomorrow I will continue with the discussion, and we are going to get to the generalized uncertainty relations, and we are going to start discussing position and momentum operators. And my goal for this course is to use all this framework of Dirac notation and operators to solve the harmonic oscillator. So maybe, I mean, it's very likely that I'll need some extra time to do so. And as I said, I will record some material because then we can, you know, I don't want to rush with the fundamental part just to get to the result where we want to you to learn. Okay. Okay. So thank you very much for your attention. And tomorrow in the morning, you are going to get the quiz, which will be online. Okay. Okay. So have a nice day, and see you tomorrow. And yeah. Bye-bye.
Hello.